I'll begin with a word of prayer. Dear Father, we thank you for this day again, Lord. We thank you for the weekend that's about to start. And I just pray that you'd help us to use this time wisely, guide my thoughts, and just help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. Let me misbehave slightly here. And it occurs to me that there's a generalization of this idea R adjoin omega, and I mean, it's not a generalization or not, but this is something called the group algebra. Group algebra is a nice way to construct rings which don't seem to appear in your book. Group algebra, so here's the deal. Given G, which is a finite group, all right, a finite group, you let, I guess I could say R sub G. It's just basically G1R, direct sum G2R, direct sum GNR. In other words, it's the set of elements, the sum I equals 1 to n of, let's say, C sub I, G sub I, such that the C sub I are in the reals. All right, I'll do the real group algebra. And so you add them in the obvious way. All right, so to add these things, add their coefficients, and you multiply them in the obvious way. Right? It's easy enough to verify that this functions as a ring, in fact, a ring with unity. You know, if G is equal to 1, you know, then 1 is naturally an element of this thing, right? Well, I mean, if you called E the identity of the group, then E would be the identity of the ring, et cetera, right? But this is actually a way to construct all kinds of interesting group rings. For example, if I look at the, you know, this group, say 1J, all right, where J squared equals to 1, right? Just, you know, that's a cyclic group of order 2, right? So the group algebra of this would be what? I mean, last class, I talked a little bit about this thing. These are the hyperbolic numbers. If you wanted to construct the 3 hyperbolic numbers in this way, what would you do? You just look at the group algebra of the group 1J, J squared, where J cubed equals to 1. Then it's pretty obvious that the group algebra here is what I called H3 last time. So I really like this idea. It's a nice way of building examples. It's a nice way of taking all the groups that you already have and creating new rings from them. Now, here's why the book doesn't talk much about these. What's the size of these rings? How big are they? They're infinite, right? These are vector spaces with a multiplication. They're algebras. But it's also interesting. I mean, it's fun. Here's one more application, then I'll get back to the book. Fun question. So if we look at, say, the hyperbolic numbers, which of course have the form, again, a plus bj, such that a and b are real, and j squared is equal to 1, then the question is, what are the possible ring isomorphisms to R cross R with the direct product. So here, A comma B, such that if we multiply AB times CD, the way it works is, AC, BD. So this is the so-called product ring of the reals. This would be a special case of the Cartesian product of rings thing I did day one. So this is often called the direct product of the reals with the reals. My claim is that those are isomorphic, okay? So how would you actually construct ring isomorphisms from here? What to me makes these problems more interesting than the ones that are typically focused on in the book is here the full weight of linear algebra comes down upon these problems because we're dealing with vector spaces. And so to find a ring isomorphism is to find a linear transformation between the vector spaces, which are also rings. And so there's other things that guide our work. Basically, generators have to go to generators, right? So the 1 has to map to the 1. What's 1 in the direct product of R and R? Yeah, it's 1, 1. Right. This is the identity in here. If we multiply that times anything in R cross R, we get back to that thing again. And the other thing, and then here's the thing that's interesting, is J, right? J has to map to something, let's say, A comma B with what? Which satisfies the same relation as J, right? J squared is equal to 1, which means whatever J maps to has to satisfy AB squared equals to 1, 1. Right? So what are the elements that have this property that they square to 1? In other words, what are the idempotents? This is the idempotent, right? This is the form E squared equals to, oh, I'm sorry, I can't do math. I'm sorry, I'm not idempotent. I always do this. Idempotent is such that it squares back to itself. This would be something else. So sorry. I'll talk about idempotence before long, don't worry. So this gives us the A squared B squared, right? 1, 1. And you can solve that, right? What are the solutions? These are real numbers. A and B are real numbers. So this gives us either A is plus or minus 1 or B is plus or minus 1, right? So what are the elements in R cross R which have J squared, which are, candidates for J in some sense? You got 1, 1. You've got minus 1, minus 1. You've got 1, minus 1. And, of course, you got minus 1, 1. But neither of the first two can be J because J is not the identity and J is not minus the identity. To say J is the minus the identity is to violate the very definition of hyperbolic numbers, which assumes a linear independence of 1 and J. I mean, that's essentially what this definition does, is it forces the group elements to be linearly independent in the group ring. It's built in. So it's got to be these. So basically, we only have two, here's the deal. If you're going to be an isomorphism, let's call it phi. Phi has to take 1 and map it to 1, 1. That's not up for grabs. And then phi's got two choices. We can either send phi of J to 1 minus 1, or we can send it to minus 1, 1. So there are just two isomorphisms, apparently. Wait a minute, you're like, whoa, 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 flag on the play there. How does that define an isomorphism? That's only two things. This is an infinite thing, right? But remember, to be a ring isomorphism means, among other things, that we have this, right? It has to preserve addition, which means that in our context, because addition is vector addition, and also it has to do what? So that's almost a linear transformation. Linear transformation has what? Scalar multiplication, yeah. I guess that I gotta be more careful about. Let's see here. So phi of C times x plus jy should be what? It's a ring, yeah, phi of C times phi of x plus jy. But why does, this is a real number, right? C is a real number. I'm talking about a real vector space structure here. And so that can be written as what? Well, how can I say this? Lemma. Phi of C is in fact equal to C. That's not quite right. Phi of C has to be, goodness gracious, I guess it has to be CC. No. Oh, now I'm confused. Curses. Well, so I'm going to leave a little mystery right here. But certainly, this much I can say. If you use these as the building blocks, you know, you can take phi of a plus bj and just map it to a times phi of 1 plus b times phi of j. I'm missing some stupid small argument that I just can't see at the moment. Then that will be a times 1, 1 plus b times, it depends on which your choice is, right? Suppose it's 1 minus 1. Then there you go. This is actually a formula that gives you the isomorphism from hyperbolic numbers to the direct product. And if you choose the other choice, then it's just a plus b, you know, b minus a, I think. No. Excuse me. Ow. That hurt. That's not cool. Yeah, I guess the other one would be what? It would be a minus b. Oh, it's the, what? I am not playing with a full deck today. Let's see here. Yeah, a minus b, a plus b, right? Just, it flips. Of course, that makes sense. I mean, the direct product, which one's first, which one's last? It's r cross r, which r is which? They're both r. So anything you can do for the direct product, there should be some sort of stupid symmetry like that for. If that's going to be an isomorphism, flipping the roles ought to also be an isomorphism, sort of by just the intrinsic symmetry of this algebra. And I'm using that word symmetry in a vague way there. So I guess the lemma I'm missing is that for an algebra isomorphism, and if I'm wrong about this lemma, there's more isomorphisms probably, okay? But I suspect that we can argue phi of well, let me not even say it, but yeah, I'm going to stop here. I said what I wanted to say, but there's a gap in my thought here. So sorry. So, getting back to the book where I'm getting behind in, let me go on. If I can find my notes. Let's see here. A good place to start for us would be, let's talk about the center of a ring. So here's a proposition. The center of a ring is going to be defined to be what? It's, to make this interesting, obviously this can't be the center with respect to the abelian group structure, right? Because then the center would always be the whole stupid thing, and that wouldn't be interesting. So by process of interesting thinking, it must be the multiplicative structure that we're talking about, right? I mean, otherwise it would just be silly. It's a definition, I suppose I don't have to justify it, but this is R in R such that RS equals to SR for all S in the ring. This is the center of a ring. If an element of the ring is in the center, it's said to be a central element. All right? So this is a subring. Let's prove it. 0 and 1 are in the center, right? Since 0 times r is equal to r times 0, which is 0, and 1 times r is equal to, well, r times 1, and they're both equal to r, right? So 0 and 1 are in the center. Suppose that we have A and B in the center of the ring, right? let S be an element of the ring, and then check it out. So if I have A minus B times S, I get AS minus BS, and then that is going to give me SA minus SB, right? Because A and B are both in the center, but then unfactor, right? So we have to use both distributivities, but you see you get this is equal to that using the properties axiom of the ring and definition of center. Therefore, A minus B is in the center. And subring test says we have to check the difference and the product are both in there. So if we look at ABS, well then that's what? That's ABS by associativity, which is ASB by the fact that B is in the center, which then, anyway, let me just get to it, SAB. So there you go. AB commutes with an arbitrary S in the ring. Therefore, AB is in the center. Thus, Z of R is subring by subring test.
Is there any notation for subring like we have for groups?
I'm shying away from that because, well, I'm just going to say it's a subset. I'll use words.
Is there a reason you don't use the
Just the thing is, we have the additive and the multiplicative structure going. I don't know. I don't see people using it, so I'm not against it, but I'm not going to do it. Wouldn't be prudent. All right. Idempotent. Definition. Again, E in R idempotent means what? E squared equals to E. So like the fundamental thing I should have, well, I mean, I gave you some examples last time, but this is like a fundamental identity for these guys. If you look at the proofs that involve idempotence, they all dance around this observation here, which is that 1 minus E is an idempotent. So like 1 minus E squared is what? Yeah, it's 1 minus E. What's that? Minus E, oh, plus E squared. But then that and that cancel. And as you guys are way ahead of me, you told me, so 1 minus E squared is 1 minus E, which is to say that 1 minus E is an idempotent. But also, this is important, E times 1 minus E, what's that equal to? Yeah, I mean, you multiply this, you get E minus E squared, which is E minus E, which is 0. And it's the same if you do it on the other side, right? I mean, so both of these guys are 0. So what does that say about a ring if it has an idempotent? If it has a non-zero idempotent, can your ring be a domain? It cannot be a domain. If it has an idempotent element, it necessarily has 0 divisors. There they are. So Theorem 6, which I will not prove, but I'll state because it's really interesting. It says if you have an idempotent element, E squared equals to E, in a ring R, all right, then you can define, as he calls it, the corner of the ring, ERE, which is the set of elements ERE, such that R is an R, all right? This gives a ring with unity E. And furthermore, it's, well, even gives, well, I'm just going to cut it off right there. He says a little bit more in the book, but this is actually very interesting. Oh, fine. So this is A in the ring, which are commuting with E. So we saw this last class. Actually, an example of this was the Z6 with the 3 times Z6. So if you have R equals to Z6, right, then you can look at E equals to 3. That has what? It has 3 times 3 equals to 3 again, right? That's an idempotent. And the corner of 3, if you will, which would be, I guess, 3 Z6 3 is just, it's just that 0 3 set. And that was in fact a ring with unity 3. So that generalizes. Anytime you have an idempotent, you can construct one of these weird, it's not a subring, right? But it's a subset which behaves as a ring. Although it doesn't have the identity. The idempotent becomes the identity in the subring. Okay. Another little proposition I should share with you, aka example 18. And it says this: if a ring R has no non-zero nilpotent elements, then all idempotents are central. So I really enjoyed the proof of this example. It was really a fun one, and just a nice encapsulation of everything that else had happened in this section up to this point. So let's go through it here. So proof. So we're going to suppose that we have an idempotent E. E squared is equal to E. All right, and we'll let R be an element of the ring. Consider, and this is the tricky part here, consider A equal to E times R times 1 minus E. All right. Which is why if I was doing this on my own, I would have a lot harder time with this probably. I don't know, maybe after you play with this for a while, it just becomes obvious this is what you should try. I'm not sure, but if you look at A squared, what do you get? Right? But you see what come up? That fundamental thing that goes to 0 for an idempotent, right? Product of E and 1 minus E, that's 0. And so this is 0, right? But if we're assuming that the ring R has no non-zero nilpotent elements, then that implies what? A must be, in fact, 0. If it squares to 0, right? Otherwise, it would be a non-zero nilpotent element. Anyway, so if A is equal to 0, then what? ER times 1 minus E is equal to 0, which is to say what? That's to say that ER is equal to ERE. I'll call that star. All right? Now, by the same token, You can look at an element B, right? Let B be very related. Like what would you choose for your B? Like almost the same thing, but what's that? Flip the E and the 1 minus, so B is equal to 1 minus E times R times E. Like that, yeah. Then B squared is 1 minus E RE, 1 minus E RE, and lo and behold, there's your 0 in the middle, so B squared is 0, which implies that B is equal to 0. So 1 minus E RE is equal to 0, which implies that RE is equal to ERE, right? You put star and star star together, notice that the ring element was arbitrary. So what have we shown? We've shown that an idempotent commutes with an arbitrary ring element. So therefore, E is in the center of the ring, which is what the claim was. All the idempotents are central. That means that they're in the center. So that was a fun one. Okay, it's less fun if you don't think to invent the A and the B, right? But there you go. All right, Theorem 7. I think we're still in section 3. I'm still hitting, you know, I guess I should erase all this. I'm still hitting odds and ends that I've missed in section 3.1. Oh, yeah. So sorry. Definitely capital R there. Theorem 7, we have for R not equal to 0, oh, I just realized I shouldn't do this today. I'm going to go on. So sorry. Something's got to give. Theorem 7 in section 3.1, I'll let you read. So, and maybe I'll do that next help session, because I have a proof which is a little bit lengthier than what's in the book. I think the book's proof for Theorem 7, not quite right. But the show must go on here. So here we are in section 3.2. This is Theorem 1. The following are equivalent for a ring R. This is Theorem 1 of section 3.2. So number 1, if AB equals to 0, then either A equals to 0 or B is equal to 0. Number 2, if AB equals to AC and A is not equal to 0, then B is equal to C. Number 3, if BA is equal to CA and A is not equal to 0, then B is equal to C. So let's see here. If you were to put this into words, what would 1, 2, and 3 be? 1 is the statement that the ring has no 0 divisors, right? 2, you might call left cancellation. 3, you might call right cancellation, right? So the claim is that these are equivalent. How would we prove that? So I'll look at the proof that 1 if and only if 3, and the proof that 1 if and only if 2 is somewhat similar. So let's look at 1 implies 3. Right? So assume 1. is true, right? So what should we do then? We should say suppose A is not equal to 0, right? And BA is equal to CA. So then what? So that gives us that BA minus CA is 0. And then we can factor A out. And then what do we have after we factored A out? What does that say? Therefore, by 1, what? Thus, either A is equal to 0 or B minus C is equal to 0. But what? But A is not equal to 0, right? Hence, B minus C has to be 0. Therefore, B is equal to C, which is what we set out to prove. There's 1 implies 3. Let's look at 3 implies 1. So we assume 3 is true, right? To prove 1, what should I do? So I should suppose that AB is equal to 0? If you want to try for a direct proof, I suppose. How do I use 3, though?
Well, you assume B equals C, and once you get to B minus C times A equals 0, you say that B minus C would have to be 0.
So you write 0 as 0 as A times 0. Or sorry, you write 0 as 0 times B.
Now that was I mean, you had 2 choices, 0 times B or B times 0, or A times 0. But is that the right one?
3, then it has to be 0 times
Yeah, the reason Sam wrote that is because he wants to use 3, which allows us to cancel things on the right. Wait a minute.
So if B equals 0, we're done. So assume B is not equal to 0.
Wait, just hold on a second. Oh, because I got B and B, so I can cancel. So, okay, so, well, here we go. So if B is equal to 0, we're done. Right? So if B is not equal to 0, then AB equals to 0 equals to 0 times B, right? Hence, A is equal to 0 by 3. And that shows that either A or B is 0. Very good. The proof that 1 is true if and only if 2 is almost the same, right? What I don't advise you trying to do is to prove 2 implies 3. Maybe you can do it. It just hurt my brain when I tried to do it. I don't know what's wrong with me, but
Now, if R is a division ring,
yeah.
this all comes very immediately.
Mm-hmm.
So is that just like a general? So, like, I mean, I think this is called. So this is a domain. Is what this is.
Right. I have not. So what's the difference between domain and integral domain? Right. Integral domains are commutative, is precisely the deal. Let's see here. So every division ring is a domain, and hence every field is an integral domain. So because a field is a commutative ring in which every element, every non-zero element has an inverse. Sorry, I'm getting off track here. So, Theorem 2 is marginally interesting. it says that the characteristic of a domain is 0 or prime. All right. So if the characteristic is 0, great, we're done. All right. So suppose the characteristic is n. And towards a contradiction, suppose that n is equal to k times m, where 1 is less than k is less than n, and 1 is less than m is less than n, right? In other words, suppose that it has the n is composite, right? So then, it's very simple to prove this. So all you got to do is look at k times 1 times m times 1 in the ring, right? We proved a class or two ago that this was km times 1, right? This is notation for k-fold additions of 1. This is notation for m-fold additions of 1. And one of our laws of ring arithmetic is that that's the same as km additions of 1, if you work it out. So anyway, this, of course, is n, right? And by definition of characteristic, this is 0, right? But then, since our domain, what does that give us? K times 1 is equal to 0, or m times 1 is equal to 0, right? And that contradicts the characteristic of the ring being n, because that would say that there's a smaller whole number than n, which if you add 1 to itself that many times, you get back to 0. Either one of these contradict the characteristic of R being n. So a ring either has prime characteristic or it has characteristic 0. Them's your choices. Excuse me, I said ring. What should I say? Domain, right? A ring could have characteristic 4. For example, Z4 is a ring with characteristic 4. But it's not a domain because it has 0 divisors. Any questions? Okay, so we will look at further examples of neat, interesting and sort of unexpected fields as we go on in here. There's a nice example, which if I had more time today I'd cover, but I'm going to go ahead and spend the rest of today talking about the most important construction in section 3.2, which is called the field of quotients. So field of quotients says something really, really interesting about any integral domain. So it becomes important when you get into the details here to assume that we have a commutative ring with no 0 divisors. This construction may or may not be possible for rings that are non-commutative. In the non-commutative case, it can be shown that essentially there is no way to do this construction. For certain examples, this is due to some Russian mathematician. He says in 1937, Anatoly Ivanovich Malsev or something like that. I'm mispronouncing his name horribly, I'm sure. On the more positive side of things, if your domain is what's called an OR domain, there's a way of doing this in the non-commutative case, but that's not something we'll actually do in here. What we'll deal with is how to construct the field of quotients for an integral domain. And this is actually really interesting because one application of this, in fact, the central application of this, is to build rational numbers carefully from integers. So here's the basic construction. So I'll try to do enough of this so that you can see how to do the rest, at least. And so the idea here is to let R be an integral domain. All right. So for us, that means a commutative ring with unity, right? And then what we're going to do is we're going to play a game which says to look at, we'll call it X because, I mean, that's what we call everything, right? Let's hear. So, and it has pairs in it. And the pairs look like R comma U, such that R and U are in the ring, and U is non-zero. So let me tell you the man behind the curtains here, so to speak. The idea is that this pair, R comma U, is going to be a formalization, and we'll use this notation in a bit. R comma U is like R over U. Now I'm going to make that precise, so I'm just saying that's the idea. You're thinking of U as being the denominator, you're thinking of R as being the numerator, and you're trying to abstract this construction of fractions. So the first thing is, when are fractions equivalent? So we're going to define an equivalence relation, equals, 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 and we'll say that RU is equivalent to RS, sorry, shouldn't have R there, is equivalent to SV, if and only if what? So man behind the curtains, right? If you want R over U to equal S over V, what would you want to impose? Right. So that defines, now I'm not deriving that, I'm defining, this is the definition, okay? Definition, this gives us an equivalence on X. That's not especially interesting, I'll just claim. You can show that equals, equals, equals is an equivalence relation on X. Okay? So being that it's an equivalence relation, that means it partitions X into equivalence classes. And it's these equivalence classes that we'd like to use the fraction notation to denote. So definition, we'll say that R over U, all right, is going to be equal to the equivalence class with representative R comma U. So this is how we define fractions. Fractions are equivalence classes of pairs, right? So once you make this definition, a straightforward application of the definition is like R over U is equal to S over V if what? Right? What does it mean for those equivalence classes to equal each other? When are two equivalence classes equal to each other? Chapter 0. If their representatives are equivalent, right? So by chapter 0, this is true if and only if RV is equal to SU, right? And of course here I'm assuming what? Yeah, U and V are not 0, of course. I mean, and R and S are in V. Well, we're assuming that R, U, S, and V are all in the ring. So that is how we construct the field of fractions. Well, we're not quite there yet, but we'll let Q be the set of these equivalence classes, R over U, such that R is in U, such that R and U are in the ring, and U is not equal to 0. All right? Now that's not, I mean, that's just a set at the moment. It's the set of equivalence classes, right? What do we call it in chapter 0? The quotient set or something, right? That terminology starts to be more natural, you know? Quotient set. Saying. But my claim is that this is a field. But to make that claim good, we have to define what? A ring structure, right? So how would you define a ring structure on this Q? Yeah, we need to say, how do you define R over U, right, plus like S over V? And you come up with a definition for that, right? And we also need to define how to multiply them, right? What do you guys think the definitions of these should be? I heard an RV plus US over UV. I like it. And this one? RS UV, yeah. Now, as I've defined these, they beg certain questions, like are these well defined, right? Because I just defined operations on equivalence classes. So you need to show that these definitions are independent of the representative, right? Then you need to show that this addition is actually associative, commutative, that it's got a zero, that it's got negatives, right? The whole deal. We have to check all the ring axioms here because this is not a subset of a known ring. This is a new ring we're building from scratch, from the ground up, from set theory, right? So you got to check all the axioms to be complete here. Which one do you want to do? Should I show it's well-defined, perhaps? What's that? Well-defined? Which one? Second one, thank you. All right, so suppose that R over U is equal to R prime over U prime, and S over V is equal to S prime over V prime, right? Then that gives us what? That gives us RU prime is equal to R prime U, and SV prime is equal to S prime V. Consider RS over UV is equal to R prime S prime over U prime V prime if and only if what? RS U prime V prime is equal to R prime S prime times UV, right? But let me call this 1. Let me call this 2. Let me call this 3. But, well, I mean, note maybe is a better word. Note 3 follows from 1 and 2, right? Am I right? What do I have to do that, though, right?
We're in an integral domain, so we can commute.
Right. That's it. So like this R and RU prime, I can trade for an R prime U, which is what I have over here, right? And I have an SV prime, which I can trade for a S prime V, which is what I need over here. And yes, this is where you see the commutivity is mission critical, right? Because I need to be able to move stuff around. So the theorem that this gives us is absolutely beautiful. It says that if R is ring, is integral domain rather, then there exists Q a field of fractions, right? A field of fractions where every U in, well, every R in R not equal to 0, has a multiplicative inverse in Q. And there's a little bit more to it. Also, the ring is identified in a natural way with the fractions. I mean, like the more full. This is stated in its all of its glory and technical nuance at the end of section 3.2. This is Theorem 5. But so this is what I was complaining about, guys, is when you look at this, what this is usually understood to mean is, well, when you write parentheses like that, it's understood to mean a field. And you see, this means that there exists a field. So to me, this, I believe, is the same as this guy. So you can talk about, so what's the difference? When you do this, you're saying you're building fractions from integer linear combinations. Like z, to me, this would mean things like this. It's fractions of those things.
Because Q is the field that Z is in.
Yeah. But it turns out that that's equivalent. You can rewrite this actually in the form C1 plus C2 square root of 2, where C1 and C2 are rational numbers. Because you have the conjugation trick, you can multiply by C minus D root 2 over C minus D root 2 and move the roots upstairs. You can always rewrite a quotient of those 1 plus root 2 things as a rational combination of them. Problem 21 in your homework will help you understand that more deeply. But anyway, I'm out of time, so I should shut up. Monday, I am going to be entirely lazy. It's up to you. You can ask me whatever you want about the test, and I will give you vagaries in response. So it'll be a waste of the day, but that is our custom.